Hi, let's talk about friction force today. Okay, so friction force. So when we talk about friction, we're talking about friction between surfaces, not air friction or fluid friction. But friction is a force that acts parallel to the surfaces that are in contact with each other. So if an object is moving one way, the friction force will oppose that motion and it will be parallel in direction to the surfaces that are in contact with each other. So think of it as it's a contact force. Now, the magnitude of the frictional force is going to depend on two things only. Okay. It's going to depend on the normal force, how hard these two forces are being pushed together. So, the normal force between the two surfaces. And a thing we call the coefficient of friction. We use this little symbol. Here's this Greek symbol. It's pronounced mu. So, the coefficient of friction mu is basically a multiplier that has a value less than one. And it's specific to um, the characteristics of the two surfaces that are involved, sort of the atomic characteristics of the two surfaces that are involved. So we have two kinds of friction. We have what we call static friction and what we call kinetic friction. So static friction, as the name implies, is something that's present only when the object is static or non-accelerate, not moving, in fact. All right. So uh, in this case, the amount of friction you're going to get is dependent on how hard you're pushing on the object. So if I have an object that's just sitting here and nothing's pushing on it, well, there's no static friction force. If there was, it would start accelerating. That doesn't make any sense. But if you start pushing on it, then what you get is a static friction pushing the opposite way. That's equal to the amount of force you're applying to it, up to a certain maximum. And once you exceed that maximum, and that maximum is defined using this equation here. So basically, the amount of frictional force associated with static friction is always going to be less than or equal to this coefficient of friction times the normal force. But once I've exceeded this value here, then all of a sudden, the object does begin to move, it sort of breaks loose, and now we have kinetic friction. So, kinetic friction is what's present when the object is in motion. And its value is going to be determined by this value here, which is basically kinetic friction is equal to the mu. And this is a different value. So, these two values of mu, you'll find there's a different one for static friction than there is for kinetic friction. But still, the equation is essentially the same, except here it's inequality. It's not less than or equal to, it is equal to. When the object is moving, this is going to define what the kinetic friction is. I know right now it means, it's kind of weird, but we'll get there. All right, let's just keep going. Okay, so the thing is, static friction is only present when the object rests. Look what we've got here. It's just sitting here. There's no acceleration. There's no applied force. Then there's no static friction. The person begins to apply, say, 100 newtons of applied force. Well, now the object is still not moving, so there must be 100 newtons of static frictional force. We have not exceeded the maximum value that's defined by that equation we talked about. The person now pushes with 500 newtons of force. Well, the static frictional force increased to 500 newtons of force. The object is still not moving. We have not exceeded that maximum value of the static frictional force. But now I push with 600. And let's just say somewhere between 500 and 600, I exceeded that value. There's no more static friction. It's gone. And now we're dealing with kinetic friction. This object is going to be moving. And the kinetic friction is going to point in the same direction. It's going to be parallel to the surface, just like static was, pointing in the opposite direction, just like static is. But it's going to have a value that's defined by that equation. That value is going to be less than the maximum value of the static frictional force. So this might help. This diagram might help. And we'll do this in lab. So think about it this way. I take a force probe and I measure how much force I'm applying to a stationary object. At first, I'm applying no force. I apply more and more and more force to it. The object is stationary, it's not moving. So I'm increasing the amount of static friction. If I stop applying force to it, the static frictional force will go to zero. If I apply more and more and more, it gets higher and higher and higher and higher until I reach a certain maximum static frictional force. And that maximum value is going to be when this equals this. So it could be this value could be less than, all right, so that's what the less than, it could be less than this value here. But when I get to that maximum value, it equals this value here. And as soon as that happens, the object sort of breaks loose and begins to slide. And once it begins to slide, we're now encountering kinetic frictional force. So if I wanted to calculate what is this maximum amount of static frictional force, I could take this equation and say, well, uh, basically this is achieved when the frictional force is divided by the normal force. So I figure out how much force I had to apply here, say 8 newtons, and then I would divide it by the normal force, and I would figure out what this value for mu is. And that value for mu is usually going to be less than or equal to 1, usually less than 1. And so let's just sort of look at this equation. Now, right now, this is the equation that says equal, so that would be for kinetic friction, but it's pretty similar for static friction. So the force of friction is, in this case, equal to, or in the case of static friction, less than or equal to mu times the normal force. So mu is what we call the coefficient of friction. It's simply a multiplier that when I multiply the normal force by that value, it will tell me what the frictional force is going to be. And as it says here, it's usually going to be less than 1. Makes sense. It should be less than the normal force applied to it. And the other thing is that the mu for kinetic friction is going to be less than the value for static friction, because usually I have to exceed static friction in order to get the object to start moving, and then it drops down to the value for the kinetic friction. So here are a list of these. These have to be experimentally determined. There's no way of just using physics to say what they're going to be. So these are basically engineering values. And what we find is, like, say I put steel on steel. Well, for the mu of static friction is going to be about 0.74 times the normal force. But once it starts sliding and we have kinetic friction, that drops down to 0.57. And so you notice in each case, depending on the two surfaces, I'll get a different value for this. And if you notice, in each case, the value for the static friction is greater than that of the kinetic friction. Right? Now, one other thing to look at is that when I have things that are very low friction, I'll have a very low multiplier. So Teflon, which is a non-stick surface, you see, has a very low value for uh, uh, both kinetic frictional and kinetic friction and static frictional coefficients of friction. Okay, now let's just try solving some problems here then, okay? So I have this object. Notice this object is moving. So I'm not dealing with static friction. I'm dealing with kinetic friction. So it's going to be equal to a value, right? So I want to know, what is the frictional force acting on this object, and how far is this object going to go before it stops? And this is what I know. I know it's traveling at 20 meters per second. It has 8 kilograms of mass, and the value for mu is 0.5. So let's just first tackle what is the frictional force. So to solve the frictional force, I would say, well, I know that uh, the frictional force is going to equal mg times this. So mg is going to be 80, and mu is 0.5. So the frictional force in this case is going to equal 40 newtons. So there's 40 newtons of force that is acting against the motion of this object, acting parallel to the surface, and that's going to cause the object to lose velocity. So now we're going to use that to figure out how far is this object going to go before it stops. So what I know now is that the frictional force is 40 newtons. So I'm going to say F equals ma. Well, the sum of the force equals ma, but the other forces are balanced and cancels out. So the only unbalanced force is frictional force. So 40 newtons equals uh, ma. So if I solve for a, I get negative 5 meters per second squared. The object is slowing down 5 meters per second squared. Once I know a, then I can use my kinematic equations to solve the problem. In this case, I don't know how long it's going to take, but I want to know how far it's going to go. So this is the kinematic equation of choice. My final value is going to be 0. I know what my initial value is, and I'm looking for delta x, and I can now fill in what a is because I was able to get that through using the mu value, and I see that it's going to travel 40 meters. How about this one? An object encounters friction as it moves to the right. Express the acceleration of the objects in terms of mu and g. All right, so I don't have any numeric values to work with here. So I would approach it this way. I'd say, first, the sum of the forces has to equal ma. I know that's true. I know that there's friction in this case, so I know that I have kinetic friction. It's in motion, so the kinetic friction force is going to equal to mu for kinetic friction times the normal force. And I also know that in this case, the normal force is equal to mg. Right? So I do know what mg. So I could rewrite this and say, well, I know the normal force in this case, and this is often going to be true. I know the normal force is usually caused by gravitation, so the normal force is mg. So I could say this: the frictional force is equal to mu mg. Get used to that one. That one happens a lot. All right. Well, therefore, I'm going to take this value here. This is the force that's causing this mass to accelerate. So I'm going to take this and substitute it into this equation here. Since it's the only unbalanced force, I'll say mu mg equals ma. Now look at this. The m's cancels out, which is an awesome thing with friction. All right, and so if I just rearrange this, I would say, well, if I'm solving for a, I'm going to say mu m over m, and I'm left with acceleration is just equal to mu g. That's pretty cool. All right, let's try this one here. So if I know that the mu of static friction, the coefficient of static friction is zero point 0.8, what is the maximum force that can be applied to this object before it begins to slide? Okay, so, all right, let's see what I'm going to do here. I know that static friction is always less than or equal to the mu times the normal force. And I do know what the normal force is here. It's 30. Okay. And I know that this is zero point 0.8. So then I know that the force of static friction is going to have to be less than or equal to 24. So if I can push it up to 24 and it won't move. So if I push it with 10, it's not going to move. If I push it with 20, it's not going to move. If I push it with 23.8, it's not going to move. But as soon as I hit 24, it's going to break loose, it's going to start to slide, and the static friction, this value is no longer going to be relevant. I'm now going to have to switch over to the mu k, the kinetic frictional force, and that will equal the normal force times the new kinetic mu. One last thing, and that is that the normal force doesn't always have to be mg. A lot of times it is just the weight of an object on a floor or on a table. That's true. But sometimes we'll have problems where we have like an object being pushed against the wall. So let's just say there's an applied force. A person is pushing a box against the wall, but that wall, the object is sliding down the wall, and I want to know how fast that box is accelerating down the wall. So in this case, mg is not going to be my normal force. My normal force is going to be the result of this here. So let's just do a free body diagram. So what I've got here is I know that the gravitational force pulling down on this, which is what's going to make it accelerate down the wall, is equal to mg, which in this case is going to be 5 times 10 is 50. I know that I'm applying a force of 100 newtons to the right towards the wall. So here's that. And I know that there's an action-reaction pair happening here because this force is acting between these two objects. So the wall is going to push outwards on the box with 100 newtons of force. So this is my normal force, not this. So then I'm going to turn around and say, all right, well, let's see. I know that my mu value, in this case, between the box and the wall is 0.2. Pretty slippery, all right? So now what I can do is I can say, well, the object I'm told is accelerating, so I want to know how fast it's accelerating. So the frictional force is going to equal the kinetic mu times the normal force. The normal force in this case is 100 newtons. So the frictional force is 20 newtons, and that frictional force is going to be operating counter to the motion of the object. The object is going to want to move this way, so frictional force is going to go in the opposite direction. So this value is going to be 20 newtons. So then I can find the sum of the forces. These ones are balanced, these ones are not. I have 50 in the downward direction and 20 in the upward direction. So I'm just going to call down, this the direction is going to go. I'm going to call that positive, so therefore the frictional force is acting in the negative. I could do it the opposite, but then I've got to say that, that this is the negative direction. I don't want to. So I got 50 newtons down, 20 newtons up, and I have a 5 kilogram object. How fast is it going to accelerate? Well, when I saw this, I see the answer is it's going to accelerate down the wall at 6 meters per second square. Okay, thanks for watching, and